Good morning. Can you hear me, Vitaly?
Yes.
Great, great. All right. I guess we can start. One thing I wanted to mention. Okay, are there questions about Monday's lecture? One thing that I wanted to mention is that I forgot to say last time that the proof of the strong maximum principle that I gave in the context of RCDK in space, I mean, that is certainly, it works, is correct, but you should know that strong maximum principle holds in much more general spaces. What it is sufficient is that the space as a measure that supports, it's doubling and supports a Poincare inequality that is sufficient to, in some sense, run the Moser iteration argument that gives a weak Harnack inequality that in turn implies the strong maximum principle, this sort of business, and there's nothing to do with the linearity of the Laplacian. So the proof is more complicated. The one that I gave, thanks to the additional, properties of the RCD space is way simpler, and the fact that we are really working with the Laplacian. But you should know that that thing works in way higher generality. A reference for that is the book by Anders and Anna Bjorn, Nonlinear Potential Theory in Metric Measure Spaces. I wanted to mention this. All right. Now, let's go on with the splitting. So from now on, X.
Nicola?
Yes.
Sorry, it's not showing, the board is dark and it's not showing individual boards. Could you
wait a
fix
second?
It's number 2,
Yeah.
I think.
Yeah, okay.
That's okay?
Yeah.
So you should see this board and this board. You see me? Yes, you see me. Okay, very well. Okay. So X is RCD 0n containing a line. Containing a line. So a line gamma, let's say, or gamma bar. So this I'm up from R into X, such that the distance between gamma T bar and gamma S is equal to S minus 2, okay? For any ES real. Okay? Okay. Can you read, Vitaly?
Yes. Wait. There was something happening with the
we
light.
were playing a bit with the light, but
Okay, yeah. No, it's fine.
okay, very well. Okay. All right. Now, let's define the Boosterman function. Actually, I have two Boosterman functions. I mean, I will follow, the outline of the proof in the smooth case. So let me define b plus of x. This is just the limit as t goes to plus infinity of t minus the distance between x and the point gamma bar t. And b minus is the the analog you have a Boosterman function as soon as you have a half line. Now here we have a line, so we do the same thing. T still goes to, let's say, to plus infinity, and then we do this, but we take the distance from the point gamma bar minus t. We go right. So what do we know about the Laplacian of these guys? Well, lemma or problem. The Laplacian of both b plus and of b minus, I claim, is less or equal than 0, on u. Let me say on u for every u, compactly, open set, relatively compact. Okay.
Bigger than or equal than 0.
Yeah, bigger or equal. Thanks. Yes,
I mean, with your conventions of Boosterman functions, right?
Yeah. Sorry. With this sign, of course, with this sign choice is greater or equal. Thank you. Absolutely. I would have been in trouble in a couple of seconds otherwise. Okay. Proof. Well, recall. So we have proved last time that the Laplacian of 1/2 distance squared from any point is less or equal than nm, for every open set, let's say, for every bounded open sets inside X, right? Now, and we also proved, let me see the distributional sense, and we also proved the chain rule for the distributional Laplacian, namely namely Laplacian of what was phi composition f, that was equal to phi prime composition f Laplacian of f plus phi second composition f df squared, right? Under suitable assumptions, let's say if f and phi are Lipschitz, phi prime and phi seconds are also, phi should be smooth in the image of f, and f is Lipschitz, and that's a distribution of Laplacian, right? So let's pick now, as phi of z, we pick the square root of twice z. This is certainly not Lipschitz, but Lipschitzianity is broken at 0 if I pick. And now I do the following: I pick an open set U, whatever it is, and let's say that I want to prove Laplacian bound for B plus, for B minus is the same. Then, given that I have a line, for sure, eventually, gamma bar t will not belong to U, for any t, sufficiently big, right? Because U is bounded, and gamma, is a line, so it's unbounded. Okay? So pick any, so fix U, pick any such t, and notice that now the function distance squared from gamma bar t is bounded from below by a positive constant in U. So I can apply the chain rule with that phi, right? And deduce that the Laplacian, distributional Laplacian of distance function from gamma t bar, okay? Well, this is equal to, let's see, phi prime with the derivative of phi. So phi prime, of course, is 1 over what is it, square root of 2z or z? I never remember. So I should the square root of 2, and then it's like this. Yes, and phi second as a sign, square root phi second is less or equal than 0, right? So this Laplacian is equal to what? Is equal to, so this is of course is the Laplacian of phi of distance squared over 2. So I have 1 over distance, right? And then I have the Laplacian of 1/2 distance squared. Okay, and then I have another term, but the other term is negative, or it is non-positive. So it is, I can write like this, right? Now this guy is less or equal than n, so this is less or equal than n times n divided by the distance gamma t bar times the reference measure on the open set U. All right. So for the same reason, the Laplacian of t minus the distance is greater or equal than this, I guess minus this on U. And this is true for all t sufficiently big. I mean, the constant, of course, you can see by the definition, there's no gradient, right? The gradient is 0. I mean, so that for trivial reasons from this we follow this. Okay. Okay. So what I want to do, I want just to send t to plus infinity, and notice that as far as I remain, on my bounded open set U, this quantity will uniformly go to 0, right? I mean, the denominator goes to plus infinity, so 1 over this guy goes uniformly to 0. And I want therefore to deduce by some limiting property that indeed the Laplacian of B plus is greater or equal than 0, right? So I just have instead to pass to the limit in the Laplacian bounds. Okay. And how do I do? Well, let me give a name to this function just to fix the idea. Let's call it them, I don't know, BT, just for brevity. And now what's the point? So dBTs are uniformly Lipschitz. So dBT, well, dBTs are uniformly Lipschitz. The Lipschitz constant of BT is always, exactly 1, in fact. Okay. And they uniformly converge in the open set U to the limit function, say B plus, as t goes to plus infinity. All right. So let me have a look to the Sobolev space, relative to this open set. Let me remind you that this is W12 of the the space U bar distance m. Okay. what happens in this sublet space? So given that the Lipschitz functions, the Lipschitz constants are uniformly bounded, and given that I also have uniform convergence, these functions are uniformly bounded in this space. Okay. So this space is invert. So up to subsequences, they must converge weakly somewhere. But the limit can only be, this weak limit can only be B plus. So I do have what I do have. I just proved that BT weakly converges in W1 to U to B plus. All right. And now fix phi. Now fix phi. Now let phi be Lipschitz on X with support of phi inside U. Okay. Let's have a look. So what I would like to do, I would like to pass the limit in the integral of grad phi grad BT. No? My question is, does this converge to the integral of grad phi grad B? If I do this, I'm done. Okay. And why is this the case? Well, for instance, this is nothing but, you can see this as for instance, this is the scalar product of phi and BT in W12 minus the scalar product in the 2. But phi is fixed. The BTs are converging, weakly in W12 and strongly, but also weakly in L2. So this thing passed the limit of this. Right. And yeah, so now I'm done, right? Because if I have phi, which is literally with support in U, let's say non-negative, then I know that the integral, by this means that the integral minus integral grad phi grad BT, well, this should be equal to the integral of phi the distributional Laplacian of BT, and this is greater or equal. You see that the integral minus n divided by this distance times phi. Yeah. But now this st, this is the distance from from gamma t bar, but as t goes to plus infinity, this now is going to 0 uniformly in this open set, right? Phi is bounded, whatever, this goes to 0, right? So we established that the integral. So this proves that the integral of minus integral grad phi grad b dm is in fact greater or equal than 0 for every phi Lipschitz non-negative with supporting U, right? And that, according to our statement the other time, shows that these functions have distributional Laplacian in any bounded open set, and this distributional Laplacian is always a non-negative. All right. Okay. So first step. Let's move on. Let me now write a corollary of this. Actually, a crucial property is that, corollary. I mean, that's a crucial proposition, but in fact, B plus B minus is identically 0. Okay. Proof. Let's give a name to this function, and let's call it f. This function is certainly, Lipschitz, in particular, is continuous, and clearly the distributional Laplacian of f. I mean, I think I never stated the property, but the distributional Laplacian is linear, okay? Because grad f grad g is linear. So because of that, this is greater or equal than 0 on any open set on U for every U bounded open set, right? So it seems we are in position to apply the maximum principle, right? So we have a function which looks like a parabola. I'd love this function to have a strict maximum. Okay, if it has a maximum. So if this function has a maximum, inside some open set U, then it's going to be bounded on U. It's going to be constant on U. Sorry. Okay. Let's have a look at this function. So who is b plus plus b minus? Well, notice that f is always non-negative. Is always non-positive. I mean, less or equal than 0 on x. But the triangle inequality. You see, because what we are, see, look at the picture. We have this line. We have a point x. Here we have gamma t. Here we have gamma minus t. And what we are doing is we are picking, this is gamma bar 0. This distance is exactly t. This distance is also exactly t. And then we have a real triangle. We are doing this distance minus this, and we are adding this distance minus this. So triangle inequality is less or equal than 0. Okay, but of course, this is also 0 along gamma. If you want, or if you want just a gamma bar 0, this is 0. Right? So now you pick as a big ball centered, say in gamma bar 0. That ball, what happens? It happens that the function is everywhere less or equal than 0, but it is equal to 0 inside the open set. Therefore, strong maximum principle, an absolutely non-trivial property, this follows. The function has to be identical. All right, great. So now we have this Boosterman function globally defined, and which is okay. It's harmonic, right? So the distributional Laplacian of this b, is both greater than 0. Sorry, the Boosterman function. So let me define. Let's say. So now let me call b plus, let's say, which is minus b minus. Okay. Now b is my Boosterman function, and of course the Laplacian of b is 0 on any open set you want, right? Just because it's both greater or equal than 0 and less or equal than 0, so it can only be 0. Okay, you should think of this function as a kind of an affine function defined on the manifold. I mean, in fact, at the end of the proof of the splitting, if you think at the proof in the smooth case, that's really what it is. We have a function which has 0 Hessian, right? Now, if you remember the proof for the splitting in the smooth case, now this step to be done is to prove is to introduce the gradient flow of this function b. Okay. Now, as much as I'd love to do the same here in this context of RCD setting, we don't know yet enough about regularity and structural theory of of RCD spaces to actually pursue this road. I have to say that with the current technology, if I had introduced the concept of regular Lagrangian flows and and also things about second order calculus, Hessians, and so on in the setting of RCD spaces, I could actually pick the regular Lagrangian gradient flow of B. But in fact, given that the particular structural properties of Boosterman function in our setting, it is way simpler to proceed in a different way and to actually use optimal transport to build the same gradient flow, but through other means. And here the key lemma, if you want, is this, or observation, is the following: is that for every real number a, the function ab is a C concave. Here the cost function is distance squared over 2. Okay. And I can tell you exactly who is the C transform. The C transform of AB is minus AB minus A squared over 2. Moreover, we have that a couple, xy belongs to the C superdifferential of AB if and only if yx belongs to the C superdifferential of minus AB, if and only if two things are true. the distance between x and y is exactly the absolute value of a, and b of x is equal to b of y plus a. All right. So what is this telling? So let's look at the picture for a moment, and then we come. I mean, the proof is two lines of inequalities, but I want to illustrate 1 second. 1 second was the picture. What does it mean that the function is C-concave? It means that its graph can be seen as an envelope, as an inf of graph of distance square functions, right? And so what this is telling is that our Boosterman function, the graph of our Boosterman function, which is, I'm thinking it as a fine, so I'm drawing it like this, is in fact the inf, of parabolas of this kind. Okay. And why is this the case? Perhaps we should think for a moment about this, about what I just drawn. If you have a distance function from a single point in an arbitrary geodesic space, the graph looks like this. Okay. Now, this is never typically not a C-concave functions, because you cannot reach with parabolas at the tip of this cone. It's too sharp. But as far as you remain a little bit far from the tip of the cone, this is certainly true. You see what I mean? And now what is happening here with the Boosterman function is that the Boosterman function is limit of distance function of this form, where I'm sending the tip to the cone to plus infinity. That's why. Okay. And then this xy belonging to the C sub differential is really speaking about the relation between the touching point of the function and the vertex of the parabola. So you see that something of this form is in place. If I want to find a parabola whose the vertex of the parabola which is touching my function b at some point, well, this should be something where b is smaller. And how much smaller? Well, precisely this. Okay. So that's in some sense the picture. Now let's go to the proof. Well, first of all, notice that given that b is 1 Lipschitz, we have that a for any x and y, abx minus aby, this is certainly less or equal than absolute value of a times distance between x and y, and this is less or equal than distance squared xy over 2 plus a squared over 2. Right? So by the way, with equality in both if and only if the distance what happens, I guess, if and only if star holds. Right? When is that you have equality over here, you want b of y to be just smaller than b of x, with difference exactly exactly the distance between x and y, and that's okay. It's a simple check. Now, because of this, now what do I do? Let me bring b of x over there, a squared over here, and I got the distance squared xy over 2 minus ab of x. This is greater or equal than minus ab of y minus a squared over 2. Right? And this is true for every x and y, so this is also true if I take here the inf over x. But this inf over x, of course, now is equal to, by definition, this is equal to AB C transform at the point y. Right? So I have established one of the two inequalities over here. Okay. How do I conclude the proof? To conclude the proof, it is now just sufficient to show that for any given y, I can find an x such that star holds. Because if that's the case, I have proved at the same time that I have equality here. So that's tell me who is the C transform. I proved that the x and y should be a couple, in the C sub differential. And once I have established this formula, it is also clear that now, being this true for any real number a, this also proves that AB is C concave, because I can apply this formula twice, you know, and get back to it, right? Make sense? All right. So now my goal, up to, you know, swapping against x and y, is given x, find the y such that this is true. And how do I do this? Well, it's very easy. You know, fix x. Let me also say and pick a positive. If a is negative, you just, you know, go in the other direction of gamma bar. And now notice the following. So for every t positive, actually, let's say bigger than a, let eta t be a curve from 0 to, you know, defined on the interval 0 distance x t bar to x, geodesic, because with unit speed, you know, from x to gamma t bar. Okay, I'm just doing this. This is my line, this is my point x, and what I'm doing, I have gamma t bar. I'm picking this guy, you know, and then this guy I will send it to t2 plus infinity. Okay, and then I define and consider the point I don't know, zt to be just eta t evaluated at time a. So this guy would be zeta t. This would be zeta t prime or t prime. Sorry. Okay. Now, given that the etas are unit speed geodesics, and I'm evaluating all of them at the same time, these guys will live on a ball of radius, you know, a centered at my point x. So they will be on a bounded ball. Now, closed bounded balls are compact in my space because my space is proper. So up to subsequences, this must have a limit. Okay. So let's say ztn converge somewhere. I call it z. Okay. And I claim that my z does the job. It is clear that the distance between z and x is exactly a. That's because, you know, this distance between x and z is always a, right? So I'm just passing to the meeting here. What about the value of b? Well, notice that the value of the value of, well, let's have a look to btn of ztn. I mean, ztn is the converging sequence. Now, this guy is equal, by definition, this is equal to tn minus the distance between ztn and gamma bar here, right? I mean, it's really, you know, let me draw it. X is gamma. And this is z here, right? Well, but now you see, I mean, that is perhaps from the picture is clear. So ztn is along this geodesic. So this distance is exactly equal. Let me rewrite it here. I have tn minus, well, this is the distance between x and gamma bar tn, okay, minus a, right? Because this is a. Right? So this is equal to btn of x minus a. And now if you let n go to plus infinity, this guy will convert to b of x. And these guy are, I mean, these btn are converging uniformly. So now the functions are converging uniformly. The points are converging. What I conclude is that b of z is equal to b of x minus a, which is what I wanted to have. All right. All right.
Isn't it plus a? Not that it matters much.
Yes, it's a plus. Sorry. Yeah. Yes. Thank you. Yeah. Thanks. And yeah. And this is the correct one. Okay. Now there is what it is, because I swapped x and y in here. So here in the beginning of the proof, you know, here given y, I want to find an x such that equality holds in here. Right? Now I called that y for some reason, I called it x here. So the given point is this, and I found another point of distance a such that this holds. You see? Make sense? Vitali?
Yeah, this is fine.
Okay. Sorry. I was okay. All right. Now here is a point that you might, if you want, is an exercise if you want to check it in the smooth case. Say that you are in a smooth setting and you consider the gradient flow of B. So you consider, you know, for any x, you consider the curve ftx, you know, such that the derivative is grad B at ftx. Either that or with the minus. Let me check. No, this one, I guess. Okay. Now, an interesting fact that it's a consequence of the, you know, properties of the Hopflux evolution is that in fact ftx belongs to the C-super differential of TB at x. That's it. You know, if you follow the flow in this case, for this Boosterman function, if you follow the flow of the gradient flow, that's the same as, you know, as ending up in the C-super differential. This has to do with the fact that the evolution via the Hopflux, if you want, this is because the evolution via the Hopflux semigroup of B is given by B plus a constant, actually B minus a constant. Okay, so the gradient of the evolution is the same as the gradient of B. So typically, when you evolve through Hopflux, you typically follow the gradient of, you know, of the evolved function. But in this case, the evolved function, thanks to this lemma, is, you know, basically the same up to a constant. Okay. Now I won't prove this, but I'm just mentioning this to say that, you know, maybe rather than picking the gradient flow that I don't know how to do, I can just use this formula. This I know. All right. So I will. So the plan now is I will define a flow by means of this formula. I will call this gradient flow just because I want to, and then later on I will sometimes try to, you know, sometimes corroborate this definition. Although I will never really define this thing. Okay, but I will have a flow, then that will do the job for the splitting. Okay. And here it is. Now at the technical level, this is an important lemma. I guess it's one of those lemmas where measure theory is a little bit involved, and, you know, one has to just pay a little bit of attention to the statement. But if you pay a little bit of attention to the statement, then the proof will be easy. Proposition. There exists a map f from R cross X into X such that for almost every X, Borel, such that for almost every X, the curve T up to ftx is continuous and satisfies ftx belongs to the C-super differential of TD at x, you know, for every T real. First of all, so there exists this map. Okay, this map is unique. meaning that if f tilde has the same properties, then for m almost every x, we have, I mean, the curves are unique. We have ftx equal f tilde tx for every t. Okay, so the curve is unique. Okay, almost surely. Moreover, the following are true. First of all, for almost every, well, I mean, the curve t to ftx is a line, so it's a geodesic if you want, for almost every x. 2, for every t and s reals, we have that ft, I mean, this is a group, what I want to say. M almost every x. And what else? Oh, yes. And for every t in R, we have that ft push forward the reference measure. This is it is absolutely continuous with respect to the reference measure, and also, you know, vice versa. All right. So these are the first regularity proof. Well, this is the first definition of our flow. At the end of the proof of the splitting, or actually midway along the proof of the splitting, we will see that this map ft, in fact, preserves the measure and is an isometry. Ft is a map from x to x. So more will be known. But this is, you know, a first regularity result. Okay. So big isometry, then all these things will be, particularly this will be defined for every x, and the group property will be true, you know, for every x and these sort of things. But for the moment, we have this, you know, measure information. Okay. Let me see. Yeah, let me begin the proof. And let me notice, and the proof of this, in order to prove this, the fact that we spent a little bit of time discussing optimal maps on RCD Kn spaces will be useful, because we know, remember that if you give me any, say, Lipschitz Kantorovich potential, I know that for almost every x there is only one guy in the C subdifferential, and only one geodesic connecting x to this only guy in the subdifferential. That's, you know, the statement of optimal maps and optimal and optimal geodesic plans in RCD-Kn. Okay, so what I know is that there exists n Borel negligible such that for every, say, t, let me say rational, and x point in my space, but not in n, there exists a unique, element in the C superdifferential of TB at x, and the unique geodesic let me call it Tx, you know, from x to, you know, the only guy in here. Huh? I mean, for any T real, I know that there exists an outside the negligible set. I have this property. So as I run, you know, T over the rationals, I make the union of these, you know, bad negligible sets. This n is my guy. Okay. Now, yeah, let me, okay, now, okay, here is a relevant point. If I pick notice, no, I claim. So I want to show that basically all these guys are aligned, okay, and then I can really draw a line passing through them. So, and the claim is that for every s in what it is, yeah, real, I mean 0, 1, if I pick, you know, the s point of this geodesic, sorry, the x, yes, okay, this guy is an element of the C superdifferential of okay. And why is this? Well, this is a direct consequence of this property. Because notice, let me observe the following, because let gamma, so if you pick gamma geodesic from x to y, with x and y satisfying this, if you pick gamma t, you know, what happens? I claim that gamma t is an element of the, actually, let me say gamma s, so that it's clear. So this is an element of the C superdifferential of S A B at x, right? And why is that the case? Well, because so I need to check that this is true for, you know, in place of y I pick gamma s, and in place of a I pick you know, SA, right? But why is this true? So what's the distance between x and this gamma s? Well, you know, gamma is a geodesic that I'm traveling just for time s. So the distance will be s times the distance between x and y. But that is, you know, a, right? And what is the value, the distance between, you know, what is b? What is b of well, in fact, let me, so yeah, b of gamma s. It's b of gamma s. Well, b of gamma s, it is you know, it is on one side because by Lipschitz property this is less or equal than b of x plus, you know, SA, right? But on the other hand, by the Lipschitz property on y, this is also greater or equal than b of y minus SA, right? But now you use that b of y is b of x, or actually b of x is b of y plus a. So this is also less or equal than b of y plus a. Now there is an error in the sign. Wait a second. What is a minus? I mean, sorry, it's just, you know, let me avoid losing time. I mean, it works. Okay. You have here, what's the picture here? You have a picture, you have a one Lipschitz function, you have 2 points whose distance is a and whose distance in the function is a. What I'm telling you is that if you pick a geodesic along such geodesic, the function is affine. You know, that's I'm putting the inequalities wrong, but you cannot have anything either more or less, otherwise you would destroy the one Lipschitz property. Okay, so this is true. Okay, and if this is true and you read this in this term, that's the conclusion. Okay. All right, but then if this is true and s, you pick s, which is not only in 0, 1, but also rational, what this is proving is that if you pick tx, this is equal to t1 of stx. Just because if s is rational, I mean, there is only one guy in this point. If x is outside, if the point is outside this negligible set. Okay. Okay, and so I can define. Let's put now for R, which is rational. Let me define f R of x just as t of well, of course these are defined as t as Rx, but this satisfies is equal to t R over Q, Qx, and this is true for every Q rational, such that R over Q is in 0, 1. Makes sense what I'm saying? Right? I mean, this point, I mean, in this rational, thanks to this property, when I run this geodesic, you know, looking rational points, I always end up on the same guy. So this is true. Okay. And because of this, I want to keep this. I now use this property to conclude that this map FR that currently is only defined for R rational. Sorry, I will finish this proof and then I take the break. That as of now is only defined for R, which is rational, can actually be extended by continuity to whole reals. So now look, what is the distance between FRx and FR prime of x, right? Well, this is by, you know, pick just, let me say that R and R prime have the same sign. So I can find the Q big enough, either positive or negative, which works for both. If they're different sign, I mean, you just play. I mean, in fact, if you want to extend by continuity, you extend either on positive and then on negative. It is clear that F0 is the identity, just because for trivial reason. So we can assume that, you know, that they have the same sign. So you see there's the distance between T R over Q, Qx, and T R prime over Q, Qx for a suitable Q. Okay, but now this is, you know, this is a geodesic in these parameters. So I know what the distance between these 2 points. This is the same as, you know, I have to take the difference between the arguments, that is R minus R prime over Q, and then I have the distance between x and, if you want, T1 Qx. Make sense? But I know exactly how much is the distance between a point and any point in its C superdifferential, because exactly this, you know. So this distance is exactly Q, because this guy T1Q, this belongs to the superdifferential, you know, of this function. Right? So this distance, this is exactly, you know, I have the Q that pops out in the denominator of the dot C. Okay, so this map that takes R and runs this number is one Lipschitz on the rationals, and therefore can be extended, you know, to a one Lipschitz map defined on the whole space. And now of course by continuity, now I know that for rational numbers, this guy, I mean, this inclusion is true for every R rational. But now by continuity, if I let R, you know, converge to an arbitrary real number, it's immediate to check. Here you have all the uniform continuities that you want, that this in fact holds true for every R real. Make sense, right? Because I need to check. If you want, you have this criterion, you see, but it's continuously in A, X and Y. So, you know. All right. So now. So I proved the existence, right? What about and this fact? Okay. What about uniqueness? Well, uniqueness, say that a field has the same property. Well, then you know that fix any real-time t. You know that ftx and ft tilde x both belong to the C superdifferential of TBX. But for almost x, this is a singleton. So they must agree, you know. So now you see that if f tilde has the same property, outside the negligible set, you must have this equality for all t rationals. But then, you know, in T, both curves are continuous, so you conclude the equality for all t reals. So existence and uniqueness is done. All right. Let me check this inequality. this, in fact, we do know. Why we do know this inequality? This is a consequence. Actually, let me take the break here. Now that's a good point. That's a good moment to take a break. And then once we have established that we have this map characterized by this continuity and this subdifferential property, and then we will see in 3 minutes why the other measures related to curvature. All right, let's take a small break. And let's wait 1 minute and then. Can you close so we start? Thanks. All right. As I was saying, now I want to prove this inequality. That once I do the push forward, we have T, I take something which is absolutely continuous with respect to M. Well, in fact, this follows. So you remember that at some point, I proved some lemma of the following form, so that if you have a pi, an optimal geodesic test plan, actually, if I have even different, so if mu t is a W2 geodesic, and mu 0 was less or equal than some constant times M, then mu t was less or equal than constant divided 1 minus t to the power n times m. You remember, as a consequence of the RCD 0 and of this 0 n condition, right? Well, but now if I want to prove this, I will. So what do? Pick mu 0 like this, and then it is sufficient to prove that ft push forward, mu zero is absolutely continuous with respect to m for any such mu zero. If I do this, by the arbitrariness of mu zero, I'm done. But why is this the case? Well, the point is in this is so first of all, we know that this map fr is obtained by following, a geodesic, at least for R which is rational. That's what we proved before. But now we know that this left-hand side is continuous in R, this right-hand side is continuous in R. So the identity fr equal, geodesic from X to, the only point in the subdifferential with the proper Q evaluated R for Q. This is true for every real number, between 0 and 1. Sorry, for every R, for every real number, for every Q rational, such that this is between 0 and 1. Sorry. But then you see that, the map that takes, X and returns T, let me put it this way. So Ts of Qx, fix Q, rational if you want, and look at the map that takes X and returns this. This is for fixed S. This is a map that, because of this property, this satisfies Ts Q dot push forward mu zero is less or equal than C times 1 minus S to the power n. Does it make any sense, this? Because this, I put it this way. So consider define mu S as Ts Q dot push forward mu zero. I claim that in S, this is a geodesic, right? And why is it a geodesic? Because in S, I'm following geodesics, and the map that takes, for S equal 1, the map that takes X and returns this only point, defined almost surely, takes values in a C subdifferential of a C concrete function. So this is a geodesic. Therefore, mu S satisfies this. Okay. But if I pick S, if now I pick S equal, you give me R, I find Q and S that S is equal to R over Q. So so this map will be FR. That's what I'm saying. But so I just proved that FR push forward mu zero is absolutely continuous with respect to M for any mu zero. Okay, make sense? Okay. In fact, in a second, this will be improved. That we will show that FT push over M is exactly equal to M if I pay a little bit more attention on what happens on the right hand side. For the moment, I'm satisfied like this. Okay. Okay, so I have this. Now let me prove that I need some space. Now I want to prove this group property. Okay, let me pick T and S, let's say positive. And
1 second,
please.
You also need the other inequality.
I will need, but I prove this. So once I prove the group property,
right,
I will have proved the other inequality, right? If I prove that F minus T, no, composed FT is the identity, I will prove it. So I need, but okay.
Got it.
So what it is that I know? So I know that the distance between Fsx and X is equal to S because of, I know that Fsx belongs to the C subdifferential of SB at X. So this distance is S, and B of X is equal to B of Fsx plus S, right? This is true for almost every X, right? And I also know, I mean, the same is true for t, okay? But now, given that I already proved this inequality, I also know that the distance between ft, okay, I could write fty, comma y, etc., for almost every y, but given that this property holds, I can put in place of y, I can put this. Now you tell me if this is clear what I'm saying. B of fsx is equal to b of ft fsx plus t, also for almost every x. Does it make any sense? I mean, this would be true. I mean, what I know is that this, if I replace fx with y, this is true for almost every y, right? But given that the push forward with fs of m is up to the with respect to m, this is also true. I can replace y with fsx, right? Make sense? No? Because take the y's such that this is false. Take the preimage of this y via fs. This set is negligible by the push forward property, right? So this is also true. Okay. Now it follows, if you add the things up, it follows that the distance between x and ft of fsx is less or equal than t plus s by just adding this and using the triangle inequality. And you know also that b of x, by just adding this right hand side, is equal to these right identities, b ft fsx plus t plus s. Right. And now it's clear. Now this distance cannot be strictly smaller, because the difference between the values of b at this point and at this point is exactly t plus s. But b is 1 Lipschitz. So the distance with these base points cannot be strictly smaller than t plus s. It is less or equal. So here, in fact, I have equality. And using again this characterization, it follows that ft of fsx belongs to the c-sub differential of t plus s b at x for almost every x, right? But we also know that for almost every x, the only guy was ft plus sx. So we proved this, at least for t and s positive. I guess that for t and s negative, that's the same. And now what I need to prove, wait a second, yeah. And now basically, in order to conclude that the group property holds for generic t and s, it is sufficient to prove that let me erase this. It is sufficient to prove that ft of f minus t x is equal to x, which is equal to f minus t ftx, almost every x, right? Because if I do this for any real number, then by playing a little bit with algebra, you basically get the group property. All right. So and why is this the case? Well, what it is that I know? I know that ftx, this belongs to the c-sub differential of tb at x, right? But by this property, this implies that x belongs to the c-sub differential of minus tb at ftx, right? And yeah, but I also know that for almost every y, there is a unique guy in this subdifferential, right? But again, ft, I mean, by the absolute continuity over there, if I have a unique element for almost every y, I have also a unique element in this term for almost every x. Okay. but the unique element is f minus t. So I mean, the only element of this guy is f minus t of ftx, right? It's the only element. So what I proved is that this, holds for almost every x. Make sense?
Sorry.
Please.
So I guess you're using here somewhere that f t star of m is absolutely continuous.
Yes. I've used it here. Well, let me repeat.
In this spot, right?
Let me repeat. So I know that for almost every y, there exists a unique guy in the C sub differential of minus tb at y, and this guy is f minus ty. You agree?
Yes. Yeah,
All right.
I think I understand what you're doing. Yes.
Yeah, exactly. And now, given that this holds for almost every y, and that t push over m is absolutely continuous with respect to m, this is also true for almost every x. I can pick, in place of y, I can pick ftx. Right? Because the set of y's for which this is false is negligible. Therefore, the set of x for which this is false is nothing but the preimage via ft of that bad set for the y's. But because of the absolute continuity, this preimage has zero measure. Okay. So if I know that, in fact, for any x is in this C sub differential, well, then for almost every x, it must be the only element. So it must be this. All right. So it's okay, Vitaly?
Yes, it's fine.
Okay, sorry, because I don't see you, so it's not clear whether. So I prove this, and then the other is the same. Okay, please.
It depends on t somehow.
Yes, it depends on t. I don't care. So look at the way I stated it. For every t and s, I'm not, this exceptional set could be ms in t. I don't know, but for any fixed t and s, right? All right. Now that I know that ft is the inverse of f minus t, I know this. I also this follows that. Right, and it remains. So I'm almost done. It remains to prove. So I prove this. I prove this. So this is okay. This is okay. It remains to prove one. Okay, but notice that by construction, I know that the restriction. So the for any capital T, this map. I know that this is a geodesic, right? Because it is the geodesic that links x to the only point in the C sub differential of whatever t capital T dx. Right? So this is a geodesic. So I need just to translate back basically, but this is I do with this property, right? So the map. So the map f, yeah, I noticed that f, what it is? Let me put 2t here. So f, what it is? T minus t, x. This is equal to ft of f minus tx, right? And then you're done, right? So for fixed capital T, then for almost every x, this map is a geodesic in the interval 0 to t. So which is the same as okay, you mentioned something about the dependent on t, but now I use the continuity. I mean, this is still a geodesic, right? It cannot be not a geodesic. I mean, don't know where is the only guy or whatever, but that's it. All right. So end of the proof. So we put our hands in this thing that I'm calling gradient flow. And now let me improve this inequality. Let me actually show.
Sorry, question.
Please.
I thought you needed to use that B is harmonic somewhere for this proof. Did you?
In this proof, not yet, because I didn't prove that ft, the push forward of the measure, is exactly the measure. But in fact, it is hidden, Vitali, and you will see now in a second. You will see in a second. It is hidden somewhere. It is hidden. The harmonicity here is hidden on the fact that what I'm using, and I will use in a second, is that the map that takes t and returns. I mean, in the smooth setting, this would be x t t. I mean, this is morally, this is what I'm calling ftx.
Yes.
Okay, but I cannot write this, but I write this. Okay, I use the fact that this is a line.
Yes, but
and in fact, and more, sorry, and more, and I use the fact that, sorry, and more, and the fact that TB is a Kantorovich potential, is C concave for any B, for any T. These two facts together encodes in particular the fact that B is harmonic. Okay, because I guess you will see in a second. So what happened if you think so? Let me give you the proof and then we comment. Okay, let me give you the proof. It's a one-line proof, in fact. Let me give you the proof.
Sorry, proof of what?
Of the following lemma. Let me state and then proof. Okay, proposition. Ft push forward m is equal to f of this. Okay, proof. And now again, recall that I will use the following fact. Recall that if pi is optimal geodesic, is an optimal geodesic plan. I mean, if you want, if pi is a lifting of a geodesic, and let's say that we know that ES push forward pi is absolutely continuous with density, let's say at S, then eta S and the point gamma S to the power of -1/n, this is greater or equal, this follows from the CD0n condition plus a little bit of essential non-branching. This is eta 0 to the -1/n gamma 0 plus S times eta 1 to the power of -1/n gamma 1. Is that okay? Pi almost everywhere. You remember this comes from, you know, disintegrating the CD0n inequality, right? And I can sort of make this disintegration because of the essential non-branching, right? Now this guy is positive. Is a density to some power times. So let me drop. The inequality is still there. So what I get, and I'm reproving once again basically this lemma that I mentioned already before, that eta S at gamma S is less or equal if I raise to the power -1/n. Raising to this power is a decreasing function, so inequality gets inverted. This is less or equal than eta 0 in gamma 0 divided 1 minus S to the power n. All right? All right, but now, so what I will prove, what is it? Yeah. Yeah, I will prove that, in fact, rather than prove this, we'll prove that for any raw probability density, you know, probability density, say we bounded support, if I write ft push forward rho m, this is, I know already that this is absolutely continuous, so let me write it rho tm. We have that rho t composition ft is equal to rho almost everywhere. If I prove this, I'm done. You see, because then start picking rho. You know, say pick a big ball, pick the reference measure. You know, restrict to this ball, possibly normalized. Look where it goes, and it's you see what happens in a smaller ball. You know, the only mass that can come over there is the one coming from the bigger ball. Am I speaking nonsense? Is it clear what I'm saying? So if you prove this for any rho, you are done. Okay. But in fact, it is sufficient to prove this for any rho, because then I apply the same trick to f minus t and I use the group property and I'm done. Okay. Okay, but now pick. So I have to do the scaling things that I'm never, and so I'm never. Yeah. So fix capital T. Very big, imagine, and pick pi. Rho is fixed. And let pi be defined as, you take them up. Let me put a dot here, t, push forward rho m. So this is the map that takes S and returns F, capital F, ST, dot, if you want. Make sense? Now, because F is built through by taking geodesics with with endpoints in the C-sub differential of a C-concave function, this is an optimal plan with marginals that are absolutely continuous. So I can apply that inequality over there. Okay. So what I know is that so let me call eta s is this. So I have this inequality, but with this inequality now in terms of my rho t, what should I do? So if I pick S, so if I pick S equal what it is, T over capital T.
Sorry, I can't
Yes.
read the formula. What do you mean by F dot T?
This one?
Yes.
So
Oh, can you read?
this is the car. So I'm saying, so this is a map. There is a parameter here S, which is not written. There's not, and so the parameter is that S goes to F of S times T, evaluated at a point that should is the one.
Right.
Make sense?
Yes.
Right. So I'm associate. So this is the one that takes a point X and returns the geodesic that takes S and returns F S capital Tx.
Fine. Yeah.
Right. So pi is optimal plan, right? So it's concentrated on geodesics and it has endpoints that are governed by separate differentials of a C-concave function. So that inequality holds, right? This inequality over here. On the other hand, clearly E0 push forward pi, this is rho m. And for this choice of S, ES push forward pi means evaluating this in S, which is little t over capital T. So this is equal to Ft push forward rho m. So this is rho t m by definition, right? But now what it is that inequality is telling me? It is telling me that rho t at ftx is less or equal than rho 0 at x divided by, I should write 1 minus s to the power n, but s is little t over capital T, right? And this is true for almost every x. But now here I'm free to pick capital T as big as I want. I can let t go to plus infinity, and so I'm done. So you see what is happening, Vitali, here.
Yeah, no, I am fine.
You're fine. Okay, you don't need.
Yes,
so harmonicity is hidden in this proof. You see?
Yes.
Is hidden. All right. Now let me. All right. So that's huge. That's huge. So this is, I don't know how to say half of the proof. I mean, this is we already split the measure. That's in sometimes what we do. Okay. We have a flow which is measure perturbed. Now our next goal is to prove that this flow is a flow of isometries, and then once we will have done that, we will have, we will use those to actually split, finally split the space. So what I want to do now is to, well, I want to write a lemma concerning calculus with this flow, and I want to which also corroborates the fact that I want to think this flow as the gradient flow of B. And here is the lemma. Let f be a Sobolev function in our space. Well, then the map that takes t and returns, f sub t, which for me is f proposition ft, seen as a map with values in L2, is Lipschitz. Moreover, if I differentiate this at 0, this converges weakly in L2 to grad f grad b. Right. So that's a way of saying that the derivative of t is grad b. Right. All right, proof. Notice that perhaps I want to remark that if f is in L2, and I define ft in the following, in this way, so this guy is also in L2 because of the measure perturbing property over there. The L2 norm of this thing is exactly equal to the L2 norm of this. So I'm just composing with a map which preserves the measure. Okay. So at least this function belongs to L2. Right? Now the Sobolev regularity here is used to deduce a regularity property in time of this. Okay. And what's the point? And basically the observation is that what we have is that f in ftx, let me go this way, f composition ft minus f. I want to say that this is less or equal than the integral from 0 to t of modulus of the f composition fs ds m almost everywhere. Why is this true? Well, pick any m tilde, absolutely with the same negligible sets as the reference measure, but m tilde is a probability measure on X. Okay, and define a test plan pi. Let me prove this. Just define the test plan pi as f dot push forward m tilde. Actually, let me see. This is less or equal. Okay. So now this is a test plan. Okay, but if this is a test plan, we know that for pi almost every gamma, we have that f, given that f is Sobolev, we have that f at gamma t minus f at gamma 0. This is less or equal than the integral from 0 to t of the minimal weak aggregate of f in gamma s dot ds. Right? But for pi almost every gamma, but this is exactly this. The cars here are 1 Lipschitz. So for us, the gamma dot is bounded by 1. In fact, it's exactly 1, but let's say it's bounded by 1. Right? Make sense? Right? So here I'm using the fact that these have, do not overlap. In fact, this function preserve the measure to be sure that this plan pi is a test. The bound on the kinetic energy is obvious because the cars are all, uniformly Lipschitz, 1 Lipschitz, but the bounded compression property comes from the measure preservation. Okay. So I have this. So let me now, if I square and integrate, so here this from 0 to 1, so from t, of course. So when I square and integrate, this is less or equal. I use Cauchy's bars. I get t times the integral from 0 to t of df squared. All right. And if I integrate in the m, I use, I can swap, the integration, and I use the fact that fs push over m is equal to m. So this is t squared, the integral of df squared of df squared, dm, right? So and that gives my Lipschitz property. You see, the L2, the squared L2 distance is bounded by t times a constant. Right. Now, what about the second property? Well, first of all, I know that this left-hand side is bounded in L2 uniform in t, right? Just because of the Lipschitz property. So up to subsequences, it must have a weak limit. Okay. Now, if I want to check that that is the weak limit, it is sufficient to check that, now that I have boundedness, it's sufficient to check that this time g, the m, is equal to the integral of grad f, grad b, g, the m, for a sufficiently large. I mean, I should prove for all g's in L2, but given that these are uniformly bounded, I can prove just for a dense set of g's. In fact, I can also prove by linearity. I can check just for g, say positive. And in fact, now with g's I pick as g bounded probability densities with bounded support. These are dense in the positive L2 functions. Right? Well, but now this is basically just the first order differentiation formula. You pick, if g is a bounded probability density, then you define pi as before, the basically f dot push forward gm. Now pi represents the gradient of b. Because it's an optimal plan, make sense what I'm saying? And this is nothing but, this is really nothing but the first order differentiation formula. Okay. I did give the definition of plan representing gradients, right? Yes. Okay. With the Macri-Brenier theorem, etc., etc. This is what is behind this proof. Okay. Right. I'm differentiating a function f, a subwhole function, in the direction of a test plan, which is also optimal, and I have a Cantor-Lorentz potential for this plan, for that test plan, which is b. Okay, and that's or minus b, whatever. I mean the correct sign. Okay, so that's what we get. All right. Let me perhaps just mention one last thing. I know that my time is almost over. Let me just mention one thing. 1.5. Do I want to mention this? Yes, I want to mention this. Otherwise, I don't have time the next time. So let me. So we have proved. That ft push over m is m. So the flow preserves the measure. Now, in order to prove that the flow is an isometry, in some way, we need to use the fact that the B has zero Hessian. Okay? Now, the fact that B has zero Hessian comes in the smooth setting, comes from Bochner identity, okay, or at least from Bochner inequality. Okay? So we need to come into play, the big guys. Bochner has to come into play in order to prove this. Now, the way this will enter into play, is so I don't really have a Bochner identity with a Hessian, at least not as now, and I don't have so I mean I might lack a little bit of regularity, but the way I will interpret Bochner inequality is in the following, and the fact that the Hessian of B is 0 comes through the following crucial lemma. for any f in W12 and t non-negative, we have that if I take the heat flow of grad f, grad b, what I get is the following, crazy commutation formula: grad of HTF dot grad. Right? If you pick f and g arbitrarily, of course, this is not true. This is totally false. Okay? This hides crucial regularity properties of B. In fact, here this is already telling, in some sense, that B has zero action and the Ricci curvature is non-negative in the direction of grad B. Okay. Let me try to convince you about. First of all, let me try to explain you what this is telling, and then let me prove this. Okay. Now, to see what this is telling, notice that for t equals 0, this is an identity. Really? So let me try to differentiate this in t, assuming that everything is smooth. This is basically telling that the Laplacian of grad f grad b is equal to grad Laplacian f dot grad b, which already looks a bit more Bochner-like. Okay. What has this to do with the Bochner identity? Well, actually, let me also mention that if you, this implies this by differentiating in t, but with the same trick that we use to prove the Bakr-Emery estimating, that this also proves this if you try to differentiate ht minus s grad hs f grad b. At least formally, if you differentiate this in s and use and you know this, you will see that the derivative of this is 0. So this guy implies this. Okay, so it's that these are equivalent. So if I want in order to convince you that this is true, at least in the smooth setting, and that this has to do with the action of B being 0, it's just sufficient to prove this. Okay, and the idea is that, so even if you only say that we only know that the Bochner inequality holds in this sense, right? In fact, we know the weak version of this in RCD setting. Okay, now the interesting point is that B, as I already mentioned this a couple of lectures ago, B satisfies the equality here. Because B has gradient which is identically 1, so this Laplacian is 0. B is harmonic, so the Laplacian is 0 in some sense. Okay, and so this is 0. So what we can do, if you have a function that satisfies the equality and inequality, you can write down the Euler-Lagrange equation. Okay, so write this for f epsilon, where f epsilon is B plus epsilon f. Okay, expand. What is it that we get? We get, let me do the computation. So we have grad b squared over 2 plus grad b grad f epsilon plus epsilon squared over 2 grad f squared, right? And this should be greater or equal than.
So sorry, question. Do we have enough regularity to?
No, this is formal. This is formal, Vitaly.
This is formal, right?
I don't have enough regularity, and that's why I don't. I mean, this is really, I'm trying to explain.
Okay, I understand.
What it is that is going on. Otherwise,
but we really don't. We can't apply Bochner inequality to f epsilon right now, right?
Say it again.
We don't have enough regularity for B to apply.
No. In fact, no. This is just for. Imagine we are in the smooth world, and I want to convince you how I can obtain this inequality in the smooth world, even if I only know the Bochner inequality. And then the proof will. I will make some technical comment on the proof. Okay. Now this is greater or equal than what? So I have. So if I put the BB here, the B part of the Laplacian here is 0 because B is harmonic. So this is really just epsilon grad B grad Laplacian f, and then I have plus epsilon squared grad f grad Laplacian f, right? But now, of course, this drops. The Laplacian of this term is 0, and I have that Laplacian. You see, now the usual trick. You divide by epsilon. If you divide by positive epsilon, the inequality remains the same. You let epsilon go to 0, and you get 1 inequality over there. If you divide by epsilon was negative, you change the the sign of the inequality. You let epsilon go to 0, you get it. Okay, and therefore you get this. Okay, Now I cannot do this, as Vitali was telling, in our setting of the RCD spaces, but still. So and you see, so perhaps let me insist. So here, in the smooth world, here there is an Hessian term and the Ricci term that I thrown away. Okay, but the fact that B satisfies the identity here is telling me that what I've thrown away, you know, in some sense, was zero in that B. So in some implicit sense, this identity, and therefore this identity already encodes the fact that the Hessian of B is zero, and you have no Ricci curvature in the direction of graph B. Okay. Of course, I could also, you know, be brave enough and expand this. In fact, I know exactly what is this guy. Perhaps let me also mention this. Let me mention this. So I know exactly who is this by you know, by, if you want, by the Boosterman identity. This is equal to the, what it is, the Hessian of B scalar product the Hessian of F, and then I have maybe then I have plus grad B grad F grad Laplacian B plus grad B grad Laplacian F plus something like the Ricci curvature the direction grad F grad B, something like this, perhaps with some factor of 2 somewhere. Okay, so now if you plug, you know, if you know that the Laplacian of B is 0, this drops out. Okay, but so now if you are telling, so what I'm telling with the identity is that, you know, this guy is equal to this guy for any F, therefore the Hessian of B is 0, and the Ricci curvature direction of grad B must be 0. You see, so that's really, you know, encoded in that inequality over there. All right. Okay, now let me actually prove quotation mark that inequality, because there is one thing that I will not prove, and then that's the following, and it is, so the plan is this, the plan of the proof is this: rather than using the Boosterman identity and the fact that B satisfies the equality in Boosterman identity, I want to use the fact that B satisfies the identity in the Batry-Emery inequality, which, you know, requires less regularity. What I want to know, what I want to use is the fact that HT of what it is, grad HT is less or equal than HT grad B. In fact, is equal to HT grad B. That's morally what I want to use. Now I'm a little bit in trouble in writing this, because I know that the heat flow is defined, say, on L2 functions, then we extended it to L1 and then infinity functions. But our Boosterman function, you know, that grows in a linear way, certainly is not in L1 nor in L infinity. There's no way I can, you know, with the current tools that I described, that I can compute HT of B. Okay. So I need to use some, you know, more estimates in order to be sure that HT of B is actually well defined. And this is a fact. It's a fact. I will not prove this, but thanks to the doubling and Poincare properties of RCD zero and spaces, again we can run the Georgi Moser-Nash scheme to get parabolic estimates on the heat flow. And you know, this has required a lot of work by, you know, the smooth setting by Grigorian and Southcost mostly. In the non-smooth one, this has been Sturm, to prove the Gaussian estimates on the heat curve. You know, Gaussian estimates. Gaussian. I will not prove this. I will just mention that, you know, rho T x, I don't remember how I denoted this, something like this. This is less or equal than some constant divided the measure of some ball radius square root Tx e to the minus some other constants distance squared xy divided by t for every txy. Okay. Now, if you have this constant, maybe depending on t, so something t to square root of t, 1 over square root of t to some power, I think, yeah, something like this. But the crucial point is that for fixed t, you know, you have something that decreases with, you know, with Gaussian sort of speed. Okay. So So the formula, you remember that we had a formula HTF at x equal the integral of Fy rho Txy dmy, right? We use this formula to extend the heat flow to L1 and L infinity. But now if you have sufficient, if you know that this decreases sufficiently fast, you can see that this formula defines an heat flow and extends the heat flow in a continuous way. 2 more minutes and then I let you go, guys. Otherwise, if I don't push a little bit, I won't be able to finish the proof of the splitting. So the heat flow, because of that, the heat flow extends continuously to the L1, the space L1 over X, where in place of the measure M, I put a way smaller measure, something like e to the minus distance from one fixed point. Fix a point X bar, pick, change the reference measure by multiplying by exponential this guy. And it's easy to see that if you have the Gaussian estimates and you have a function which is in L1 of this space, then this integral is well defined and this continues with respect to delta 1. It's a computation, right? Because the Gaussian estimates, basically what this is telling is that f can increase exponentially and still remain in L1. But the Gaussian estimate, they have e to the minus distance squared. So that's kills off that growth, and you remain with something which is integrable and whose integrable is bounded in terms of the guy. Right? Now, why this matters? Because the Boosterman function certainly belongs to this space. It increases linearly, which is way less than exponentially, right? And once you have this, you can also prove, and perhaps this is a bit, I hope a little bit more, at least makes a little bit of sense, that HT of B is actually B. From, this follows from the harmonicity, from the Laplacian of B is 0. At least this is expected, right? The proof of this fact is an unexpiring, sequence of computations based on Gaussian estimates and decreases. So there's nothing, conceptually hard. It's just that you write down, if this is 0, you cut off. Okay, how much will be the Laplacian of the cutoff? Okay, depends on how you cut them off. But you have these, these Gaussian estimates, so this cutoff is not that, huge, etc., etc. All right, now this identity is trivially true. I know that this is true because now HT of B is B, so that's gradient of B. This is gradient of B, but the gradient of B is identically 1, so this is 1 equal 1. Okay, and more generally, you can by an approximation argument, if you fix your preferred software function f, and you put as before, you put f epsilon B plus epsilon f, again with a truncation, what I claim is that we do know that the minimum weak upper gradient of HT f epsilon is less or equal than HT, the weak upper gradient, yes, of f epsilon. I mean, this we already, if f epsilon was in W12, this, squared. Yeah, I mean, here I was lucky because everything was constant. I forgot this. Okay. If f epsilon was actually in W12, we already knew this. Now, f epsilon is not in W12 because there is a B in here, but you multiply by a cutoff, you write this inequality, you let the cutoff go to plus infinity, you use this continuity property, and you get this. There's nothing hard in that. Okay. Now, and now I'm concluding. So I know that fixed t for any epsilon, this is an inequality, and now I just expand. I do the same trick that I've done for the Bochner, but now I do this for the Bakri-Emery estimate. And the Bakri-Emery estimate, I use the fact that let me expand both sides. Who is the minimal weak upper gradient of B plus epsilon f squared? Well, this is, I know, this is, I have polarization, right? So this is dB squared. plus 2 epsilon grad B grad F plus epsilon squared dF squared. Okay, and who is the minimum weak upper gradient of HT of this guy? Well, I mean, it's the same thing. This is the minimum weak upper gradient of HT of B, which is B, squared, plus 2 epsilon grad HT of B, which is B, times grad HT of F, okay, plus epsilon squared d HTF squared. Okay, but then again, you know that if you apply the HT to this guy, you obtain something which is greater or equal than this. Now the terms with B squared they drop out because HT of a constant is constant, and you remain with 2 epsilon HT grad B grad F plus epsilon squared HT dF squared. This is always greater or equal than 2 epsilon grad B grad HTF plus epsilon squared d HTF squared. This is true. You fix your Sobolev function F. This is true for any epsilon and for any t. But now you see, as usual, you divide by epsilon positive, you let epsilon go to 0, you get one of the two inequalities. Divide by epsilon negative, it's really the Euler-Lagrange equation for B. Just define that. Okay. So end of the proof. So on Monday, so I'm sorry that I cannot. I mean entering into these details of the Gaussian estimates and the actual proof of the Bakry-Emery inequality. So what I need is this inequality for this sort of F epsilon, which it's a matter of writing it for cutoff for function multiplied by cutoff, and I have to check that when I let the cutoff go to plus infinity, the inequality is still valid. This require. I mean, it's really just based on a series of estimates based on Gaussian bound. There is nothing other than that. But that is extremely time consuming, and I think not really expiring. So what I will start. So I take this as proved for starting from the next lectures on Monday, and I will use this to prove that the gradient flow of B crosses the distance. Okay, which is the crucial part of the split. All right. Okay, that's it. See you on Monday. Bye, Vitaly.